Hello all and welcome back. So in this video, we are going to continue our discussion on complexity analysis and understand about asymptotic analysis and notation. So let's get started. Now the main idea of my asymptotic notation or analysis is that I want to actually measure the efficiency of my algorithm, okay? And I want to make sure that it doesn't depend on machine specific constraints or constants, and it doesn't require an algorithm to be implemented. Now, if you will understand, these were actually the things which I made you understand before actually introducing what asymptotic analysis is. We have seen that how machine specific constants or constraints can have an effect which is difficult to measure and is very random. Along with that, of course, if you will be implementing each and every algorithm, that is not feasible at all, right? So what asymptotic analysis say is that we want to figure out the efficiency of our algorithm without having it getting affected by the machines, and also we don't want to implement each and every algorithm which we want to actually test on. So for that particular case, asymptotic notations have been defined, and asymptotic notations are mathematical tools to represent time complexity of our algorithm. Now the understanding behind them is exactly the same, that for my particular algorithm which I have written, what exactly or how exactly does my time depends on the input, but in terms of order, right? We are not actually interested in the specific exact time which my algorithm is going to take, okay? But rather I want to understand that how many operations are going to get performed and exactly how does that relate to our input, whether it's a linear relation or quadratic relation and many other relation which we are going to study, okay? So asymptotic notations are a little bit required to be understood because they are asked in exams and maybe an interviewer can ask you to explain the same. So I'm going to explain you that with an intuition so that you always remember that there are three major asymptotic notations as we have in the screen: big O, omega and theta. So big O is actually denoted by O and it's the worst case complexity. Now this is actually something which you will be using the most, right? This is the complexity which always the interviewer is expecting you to tell whenever you write any algorithm. Again, we are going to see how we can find the same out. This you can actually think of that if let's say you are a runner, or let's say some runner is there, he says that hey, for running this 100 kilometers, for running this 100 meters, in worst case I might take 10 minutes, okay? I will not take more than 10 minutes no matter what, okay? So this is what we say is a big O notation or big O time complexity. That is the worst case complexity, right? So your runner will never take more than 20 minutes for those 100 meter no matter what. In a similar manner, let's say if you have written any algorithm, okay, that algorithm says that hey, no matter how much I actually work, my complexity, okay, it will always be dependent on linearly on your input size, right? So if you are giving me, let's say 100 elements, an array of 100 elements, okay, and if you are giving me an element of 1000 elements, then I'm going to change, or my time which I might take is going to change linearly. That is what the big O notation basically says, okay? The second one is omega notation. Again, that's the best case, okay? So it's actually, let's say Usain Bolt is kind of doing a run where he says that hey, for this 100 meter I can complete the same in 10 seconds. That's the best case scenario, okay? Best case scenario we take whenever we have in our input, okay? Let's say whenever we have in our input the best case which is possible. For example, let's say you give the sorted array only to a sorting algorithm, okay? So on that case, how your algorithm is going to perform? Is it going to take the same amount of time, or is it not? Is it actually going to take a different time? So a very good example for this is when we compare insertion sort, right? If you will give your insertion sort a sorted array, then it's going to take a much less time, whereas bubble sort still have to do all the same work because insertion sort will not be doing those swappings. If you have an idea, like we have done this insertion and bubble sort already, right? Bubble sort still have to make sure that we do all the sorting, okay? But insertion sort, because it assumes that okay, some half of your list is actually already sorted, it will not be doing those swappings, right? But bubble sort will have to do all the work, right? Or you can also assume for merge sort as well, where no matter if the array is sorted or not, it will still be dividing. So in the best case scenario, maybe insertion sort is faster than merge sort, but then again, we have to assume that yes, we are not Usain Bolt. So we have to actually think on the worst case scenario which we can take, which we can work on. Similarly, the last one is the theta notation. Theta notation is the one which is the average case scenario, which we say that, okay, in average time, this is the amount of time which my algorithm is going to take. So again, it is in middle of your best and the worst case, right? A runner who says that, hey, in an average, I can cover this 100 meter in, let's say, 10 minutes. That is what my average case is. So that is what is known as your theta notation. Okay, everyone. So I hope with that, these notations are clear. Now we are going to actually learn a lot more deep into that. And for some algorithms, we are going to find them as well. Just always remember that we are actually going to use asymptotic analysis, and via these notations, we are going to actually tell how good or bad my algorithm is in time complexity with respect to the input size. So that is what my overall now idea is. I have tried to make sure that I build this intuition in you via first 3-4 classes instead of directly introducing them. You will see that most of the things which we do here, right, that is something which we have seen practically by running different analysis, by seeing the graphs, so that we have this idea clear that yes, this is the kind of analysis which is feasible in finding out the complexities of our algorithm, right? So again, I'm gonna make sure that we discuss a lots of examples going forward, so that this whole way through which we find these complexities is a lot more clear to you. So let's meet in the next few classes and master the art of finding out the time complexity. Okay, thank you.